Mhm. Okay, hello everyone in a new video. So in this one we are going to start chapter 4, which is the chapter of resistors for grade 10 students. So this is part 1, and let me write the title of this chapter, which is given by the resistors. Now previously we have studied in chapter 2 different laws related to voltages. Then in chapter 3 we have studied different laws related to currents, and yet we haven't seen any explicit relation between both. This relation will be apparent in the case of electric components that obeys Ohm's law, and they are given by the resistor. So let me start by section number 1, which is the resistor. Then idea number 1 is the symbol. The symbol of the resistor is given by this, or even this. Okay, so as we can notice that the resistor is made up of two terminals, and these terminals are identical. We don't distinguish between the positive pole and the negative pole. So what is the resistor? The resistor is an electric component that protects other electric components by limiting the flow of the electric current. Okay. Now this corresponds for the role of the resistor. So the resistor was basically invented in order to protect other electric components from burning out. Now also let me say that the resistor transforms electric energy into thermal energy. And by the thermal energy we mean the heat. And idea number 4 is that each resistor is characterized by its resistance R. Okay, and we know that the unit of R is given by ohms, as we shall see. And now let me directly jump or move on to section number 2, which is given by Ohm's law. Now suppose here we have the following electric component, which is the resistor. So recall that the symbol of the resistor is given by that, or even this. So this is the resistor R. These are the terminals of the resistor. Now suppose that the applied voltage of the resistor here is given by U, and it's being traversed by a current I. Then till this moment we haven't seen any explicit relation between U and I. Now let's say that According to Ohm's law, we have that U is equal to R multiplied by I. So this relation relates the following two quantities U and I, and we have that R is equal to the ratio U divided by I. And let me say that where U is the applied voltage across R, and its unit is V, which stands for volts in the SI. So U is the applied voltage or the potential difference, and I is the electric current across R, and its unit is given by A, which stands for amperes. And finally, R, which can be defined by the ratio U divided by I. R is the resistance, and its SI unit is given as the resistance of R, let's say, and its resistance given by omega, which stands for omega. Okay, so notice that. Now let me also consider the following note. Now U is equal to Ri, which means that I and R are inversely proportional. Then when R increases, the value of I decreases, for the same applied voltage U. Okay, so whenever we increase the value of R, then the value of I decrease. For this reason, R stands for resistance, which means it is resisting the increase in the current I. Okay, so whenever R increases, the value of I will decrease. So in this case, let me consider the following examples. Now suppose here we have the following electric circuit. So this is a resistor R, and the value of the current I traversing the circuit is given by, say for example, 0.5 amperes, and the value of R is equal to say for example 10 ohms. Then what is the value of the voltage U of the battery, say for example? Then we can say apply Ohm's law to R. So U is equal to R multiplied by I the value of R is given by 10 and the value of I is given by 0.5. So this is equal to 5. Since both R and I are expressed in the SI, so the value of U would be expressed in the SI, which is volts. Then U is equal to 5 volts. And here we are observing that whenever we know the value of the current I and this component is a resistor, we can determine the value of U. Now let's consider the following example, which is important. Or before doing so we have the same electric circuit. And let's say that here in this case the voltage is equal to 12 volts and the current I traversing the circuit is given by 0.5 amperes, and we know that this is a resistor R, and we are interested in determining the value of R. So let's say apply Ohm's law to R. Then U is equal to R multiplied by I, knowing that we are interested in determining the value of R. Then R is given by eventually U divided by I, and R is equal to 12 divided by 0.5, which is equal to 24. Notice that because U and I are expressed in the SI, so the value of R will be in the SI, which is ohms. Then the value of R is equal to 24 ohms. But now let's study more this equation or this relation. And let me write here that we have calculated R to be U divided by I, which is equal to 12 divided by 0.5. Now what does omega stands for actually? So notice that here U is given by volts and I is given by ampere. So the SI unit of R is given by, so the value is given by 24, but the SI unit is given by volts per ampere, and this unit is denoted by ohms. So here what we notice that omega, which is ohms, is identified by volts per amperes. So whenever we say that we have a resistor given by 24 ohms, so this is equal to 24 voltage per amperes. So for this resistor, what does 24 volts per amperes represent? So this resistor have a value of 24 ohms, which means 24 volts per ampere, which means that in order to increase the value of the current by 1 ampere, we must increase the voltage by 24 volts. Okay, so if we need to increase the current, I repeat, by 1 ampere, we need to have an applied voltage given by 24 volts. So suppose that, so this is example 3, or we are still in the same example. If we have a resistor R and the value of this resistance is given by 100 ohms, then how do we interpret this value? So we know that 100 ohms is equal to 100 volts per ampere, which means that in order for this resistor to be traversed by current I, which is given by 1 amperes, then we must apply a voltage of 100 volts. Okay, because for each 1 ampere we have a value of 100 volts. Now suppose that we need to increase the current not by 1 ampere, by 2 amperes. But we know that in this case each 100 ohms, which is given by 100 volts per ampere, in order to increase the current by 1 ampere, we need to apply a voltage or a tension given by 100 volts. What about 2 amperes? Therefore, in this case, we need to apply a voltage given by U is equal to 200 volts. And this is obvious because this is coming from Ohm's law, because U is equal to R multiplied by I, 100 multiplied by the value of the current, which is given by 2, it will give us 200 volts. Now we should understand R, the unit omega, which is given by volts per ampere. In order to increase the current by a certain value, we need to increase the voltage, okay? And each resistor is characterized by this number. And now let me also give the following note, which is extremely important. Now we are also talking about the resistor. So suppose that the reverse current I, this is I, and this is R. Now according to Ohm's law, U is equal to Ri, Ohm's law. So this is the applied voltage U, but we are used to the fact that the voltage is not labeled by U but labeled through points. So suppose that this is the point A and this is the point B. Now we need to check, or we need to determine whether this voltage is UAB or UBA. Now because this quantity is positive, okay, so this voltage is positive. Now here we can talk about the voltages UAB or UBA, because UAB is the voltage from the positive. So UAB is in the direction of flow of the current from A to B, which means that the potential at the point A is greater than the potential at the point B, which means that VA minus VB is positive, which means that UAB is positive. So in this case, this is positive and this is negative. So always, whenever we are using Ohm's law, these points here, A and B, are in the true direction of the electric current, or in the positive direction of the electric current, okay? So we cannot say here that UBA is equal to Ri, because simply this quantity is positive and this quantity according to the flow of the direction of the current is negative. So in this case, we always say that according to Ohm's law, U is equal to Ri, in which AB represents the direction of flow of the current, okay? So this is it for Ohm's law. Now let me move to the other section, which is also important, the equivalent resistance. This is given by grouping of resistors. So what is an equivalent resistance? Is a resistor that can replace a grouping of resistors such that it has the same effect. Now this statement here is very critical, the same effect. Now whenever we discuss the equivalent resistance in both cases, now I will explain more what is meant by this. Now let me say that the grouping of resistor may have two different forms. It may be in series or in parallel. So first let me consider the first case, which is given by series grouping. Now suppose here that we have two resistors that are in series. So this is the terminal A, this is the terminal B, and this is the terminal C. Now the equivalent resistors, if this is R1 and this is R2, the equivalent resistance, which is a resistor that replaces the points, resistors R1 and R2, in this case the point B will disappear. So this is the point A, and this is the point C, and R equivalent in this case in terms of R1 and R2 is given by R1 plus R2. Okay, so simply R1 and R2 can be replaced by a single resistance given by R equivalent is equal to R1 plus R2. Okay, and as you can notice that in this case the point B disappears. Now what do I mean by they have the same effect? So in this case here, if we have a current I traversing this branch, we can calculate the voltage UAC, which is the voltage UAB plus UBC. In this case, because this resistor is equivalent to these two resistors, if we have the same current I, then we will have the same applied voltage, which is given by UAC is given by R equivalent multiplied by I. Okay, so by the same effect we mean let me put it this way around. So if we have the same voltage UAC, then this branch will be traversed by current I. Now the equivalent resistance means that if we apply the same voltage UAC, then it will be traversed by a current I. But what is interesting, that the value of this current will be equal to the value of this current. So when we have the same applied voltage, then it will be traversed by the same current. Now in the case of parallel grouping, so also this formula applies also if we have another resistor here in series. So we have 3 resistors. Now this one can be simply generalized by adding plus R3. Now in the case of parallel grouping, suppose here we have 2 resistors that are in parallel. So why these 2 resistors are in parallel? Because the 2 terminals are in common. This is the point A and this is the point B. So notice that in this case no point will disappear, and this is R equivalent that replaces R1 and R2. But now what's the relation between R equivalent R1 and R2 is that 1 over R equivalent is equal to 1 over R1 plus 1 over R2. Okay, so another formula we have seen previously in grade 9 is that one can say that R equivalent is equal to R1 multiplied by R2 divided by R1 plus R2. This formula only holds true if we have only 2 resistors in parallel. If we have more than 2 resistors in parallel, for example 3 resistors, this formula will break down. Okay, now what happens in this case if we have 3 resistors in parallel? If we have 3 resistors in parallel like this, and this is R3, this formula then it's given by 1 over R equivalent is given by 1 over R1 plus 1 over R2 plus 1 over R3. If you are using the formula which is given by R equivalent is equal to R1 multiplied by R2 divided by R1 plus R2, we cannot say that R equivalent, for example, in the case of 3 parallel resistors is given by R1, R2, R3 multiplied by R1 plus R2 plus R3. Okay, this is completely wrong. For this reason, we will not use this formula at all because it is difficult to generalize although maybe in the coming parts we will generalize this formula, but for the time being we will use this formula in the case where we have parallel grouping. Okay, now as application on what we have explained, let's consider the following exercises. Let me start by exercise number 1. So in each of the following cases we need to determine the equivalent resistance. Okay, so let's start by figure A. So suppose that this is R1 and this is R2. Now always whenever we are calculating equivalent resistance, first we need to mention whether these resistors are in series or in parallel. So notice that they have only one terminal in common, so this is in series. Let me say that this is the point A, this is the point B, and this is the point C, and let me say that R1 and R2 are in series. So in this case the equivalent resistance is given by R1 plus R2. Now the value of R1 is given by 10 and the value of R2 is given by 30. Plugging this on the calculator, then the value of R equivalent is given by 40 ohms. And whenever we determine an equivalent resistance, it is always convenient to redraw the equivalent resistance replacing the grouping. So the point B will disappear, this is the point A, and this is the point C, and this is R equivalent. So done with figure A. Now with figure B, let me say that this is R1, this is R2, and this is R3. Now notice that, let me say that this is A, this is B, this is C, and this is D. Notice that in this case R1, 2, and 3 are in series. So let me say R1, R2, and R3 are in series. Then in this case the equivalent resistance is given by R1 plus R2 plus R3, which is given by 1 plus 10 plus 100, which is equal to 111. But notice that here each of these resistance are expressed in kilo ohms. Then we are adding quantities. All of these are expressed in kilo ohms, as if we are saying 1 kilo ohms plus 10 kilo ohms plus 100 kilo ohms. Then the answer will be expressed in kilo ohms. And we know that kilo ohms is not the SI unit of resistance. In order to convert from kilo ohms to ohms, we need to multiply by 1000. So this is given by 111,000 ohms. Then R equivalent is given by 111,000 ohms. And whenever we determine an equivalent resistance, it is convenient to represent this resistor instead of the grouping. So eventually here in this case the points B and C will disappear and we are left with A and D. And this is R equivalent, which is given by 111,000 ohms. So this is for figure B. Now as for figure C, we are done with figure A. Now in figure C, so this is R1 and this is R2. Let's say that this is the point A and this is the point B. Notice that in this case R1 and R2, they are in parallel because they have two terminals in common. So always whenever we are calculating equivalent resistance, first we must say the grouping, that R1 and R2 are in parallel. So usually this statement we give it half a mark. Then in this case the equivalent resistance is given by 1 over R equivalent is equal to 1 over R1 plus 1 over R2, which is equal to 1 over 20 plus 1 over 20. Now here you need to be very careful because we are adding two fractions, and whenever we are adding two fractions you need to consider two different things. First one, that we need to consider the common denominator, in this case the R20, and also you need to consider that the answer of the fraction must be in the simplest form, or simply you plug this expression on the calculator and the value is given by 1 over 10. But notice that in this case we have determined the value of 1 over R equivalent and not R equivalent. So we are interested in determining R equivalent, then simply we cross multiply and the value of R equivalent is given by 10 ohms. And let's represent this resistor instead of the grouping. So this is R equivalent, this is the point A, and this is the point B, and this is R equivalent. And we are done with figure C. Now as for figure D, so let me say that this is R1, this is R2, and this is R3. This is the point A and this is the point B. Notice that R1, R2 and R3 are in parallel. So let me say that R1, R2 and R3 are in parallel. Why they are in parallel? Because three resistors have two terminals in common. They are given by A and B, and in this case the corresponding formula is given by 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Now the value of R1 is given by 20 and the value of R2 is given by 20 and the value of R3 is given by 10. Now here also, as I have mentioned, we are adding fractions. We are not usually performing usual addition. So you need to consider the common denominator and the simplest form, or simply you plug this expression on the calculator. Then it's given by 1 over 5. But notice that this is not the value of R equivalent, this is the value of 1 over R equivalent. Then 1 over R equivalent is equal to 1 divided by 5. Now we are interested in determining R equivalent. So if you cross multiply, then the value of R equivalent is given by 5. Now what about the This is very tricky. Notice that all of the previous values of R that we have used are given by kilo ohms. So the value in this case of R equivalent is given by kilo ohms. But we know that kilo ohms is not the SI unit of the resistance. In order to convert from kilo ohms to ohms, we need to multiply by 1000. So this is given by 5000 ohms. So R equivalent is given by 5000 ohms. And we are done with figure D. Now as for figure E, let me say that this is R1 and this is R2 and this is R3. Okay, this is the point A, this is the point B. Here in figure D I have forgot to represent the equivalent resistance instead of the groupings given by R1, R2 and R3. This is the point A and this is the point B and this is R equivalent. So this technique will be clarified later when solving problems and not direct applications as this exercise. Okay, now regarding figure E, now and here let me say the following important remark. We cannot say that R1 and R3 are in series because they have another terminal in common, that of R2. So R1 is not in series with R3. This is completely wrong. Similarly, we cannot say that R2 is in series with R3 because they have another terminal here. So we cannot say that R2 is in series with R3. This is completely wrong, okay? So in order to calculate the grouping, first we will determine the equivalent resistance corresponding for R1 and R2 because they are in parallel. Then let me say that R1 and R2 are in parallel. Then in this case, 1 over R12, what does R12? R12 is the equivalent resistance only replacing R1 and R2 and not the final equivalent resistance, which is given by 1 over R1 plus 1 over R2, which is equal to 1 over 60 plus 1 over 15. Now plugging this expression on the calculator, we have that it's given by 1 over 12. Now what does this value represent? This value represents the value of 1 over R2, and we are interested in determining the value of R12. Then in this case R12 is equal to 12, but notice that because these are expressed in kilo ohms, then the value of R12 will be expressed in kilo ohms. Now let's replace R12 in this grouping, so it will replace only the resistors R1 and R2. Therefore the points A, B and C will remain present. So this is the point A, this is the point B, and this is the point C. This is R12 is equal to 12 kilo ohms, and this is R3 which is equal to 10 kilo ohms. But notice that the equivalent resistor is the resistor, it is a single resistor that can replace a grouping of resistors. So in this case we didn't answer the question and we didn't determine the equivalent resistance. Now we need to say that R1, 2 and R3 are in series. Then the final equivalent resistance is given by R equivalent is equal to R12 plus R3. The value of R12 is given by 12 and the value of R3 is given by 10, which is equal to 22. Now notice that because R12 and R3 are expressed in kilo ohms, then the value of R equivalent will be expressed in kilo ohms. And for this reason I didn't convert kilo ohms here to ohms. I left it kilo ohms because I know that I will add it later to kilo ohms and the final answer will be kilo ohms. Now in this case kilo ohms is not the SI unit of resistance. In order to convert from kilo ohms to ohms, we multiply by 1000. Then 22 multiplied by 1000 is given by 22,000 ohms. Then R equivalent is given by 22,000 ohms. And we are done with figure E. Now let's move to the final figure, which is figure F. Then in figure F, let me label the following resistors. This is R1, this is R2, and this is R3. Let me say that this is the point A, and this is the point B, this is the point C. Okay. Now regarding the groupings, we cannot say that R1 and R3 are in parallel because the terminal B is not connected to C. Similarly, we cannot say that R2 and R3 are in parallel because point B and A are disconnected, they are not joined together, okay? So in order to start, first we need to consider that R1 and R2 are in series. In this case, the equivalent resistance, which will be denoted by R12, sorry, here I didn't represent an equivalent resistance for figure E. The equivalent resistance will be like this. This is the point A, the point B will disappear, and this is the point C, and R equivalent in the SI is given by 22,000 ohms. Now R12 back to here is given by 50, which is R1, plus R2, which is equal to 50, plus 10, which is equal to 60. Since both this and this are expressed in kilo ohms, then this will be expressed in kilo ohms. No need to convert this to ohms because yet this doesn't represent the final answer. Then R12 is equal to 60 kilo ohms. Now let's replace this equivalent resistance here in the grouping. It will replace the resistors R1 and R2, then the point B will disappear. This is the point A, this is the point C. This is R12 is equal to 60 kilo ohms. And this is R3 is equal to 30 kilo ohms. Notice that I haven't converted this to ohms because yet we didn't finish the final resistance, which is the equivalent resistance, and this doesn't represent the equivalent resistance because we know that the equivalent resistance is a single resistor that can replace a grouping of resistors. Now in this case, notice that it's very clear that R12 and R3 are in parallel. Then the formula of the equivalent resistance is given by 1 over R equivalent is equal to 1 over R12 plus 1 over R3. Now the value of R12 that we have calculated is given by 60, and the value of R3 is given by 30. Now plugging this expression on the calculator, then the sum of these two fractions is given by 1 over 20. Now 1 over 20, this value represents the value of 1 over R equivalent, and we are interested in determining the value of R equivalent. So if we cross multiply, then R equivalent is equal to 20. Since both this and this are expressed in kilo ohms, then the value of R equivalent will be expressed in kilo ohms. And we know that kilo ohms is not the SI unit of resistance. In order to convert from kilo ohms to ohms, we multiply by 1000. Then R equivalent is equal to 20,000. And whenever we calculate an equivalent resistance, it's convenient to represent it. So all of these three resistors that have changed to 2 will boil down to only single resistor across the terminals A and C, having an equivalent resistance is given by 20,000 ohms, which is equal to 20 kilo ohms. So that's it for me in this video, guys. In the next part 2, we'll complete solving exercises on this chapter and complete the explanation as well.